Did I pronounce it?
Yes.
Roughly? And Gregorio received his PhD in information engineering from the University of Pisa in 2002. And he's been a visiting scholar at the University of California, Los Angeles, and a researcher with the SNIT. Currently, he's an assistant professor at the Department of Information Engineering at the University of Pisa. And he's been involved in several research projects funded by NSF, DARPA, and the European Union. And his main research interests are traffic measurements and analysis in high-speed networks. So, please.
Thank you, Stefan. So this paper is about the extension of a well-known library, the pcap library, for widely used for traffic capturing. And let's do this way. And let me first spend a few words to introduce this work. Basically, there's a fact now that today's hardware, commodity hardware, is more than okay for running high-speed network applications. So we have network cards with multiple interrupt lines that can easily, that can take 10, 50, 100 gigabits per second. And we have CPUs, powerful CPUs with multi-core on board. So, I mean, from the hardware point of view, there is no real problem dealing with huge bunch of traffic. From a software point of view, still we don't have a lot of problem because we have plenty of I/O accelerated frameworks to capture traffic at speed. We have libpcap, pfring, netmap, pfq. So we have a lot of tools in our hands to instrument a commodity PC for being easily a routers or a monitoring system. The other point is, what about the application? Are they actually able to catch up with high traffic rates like the ones that we have on multi-gigabit links? So basically, it's a fact that non-trivial application may spend order of magnitudes of thousands of CPU clock cycles per packet for their computation. For example, think about the packet inspection system. And this means, for example, a 3 gigahertz CPU, we have about 3 megapacket per second as a budget. And we have the CPU frequency, which is more or less saturated. So in all these cases where the bottleneck is the application itself, I mean, the application has to make a lot of computation and cannot catch up with the rhythm, with the traffic pace. The only solution looks like being the computational parallelism. As such, application should be ideally multi-threaded or at least multi-process ready. And of course, the I/O framework must support packet fan-out. So that is, packet fan-out meaning the distribution of packet across different workers, say thread or processes. Let's have a look at the Linux socket. Linux socket actually supports packet fan-out. Basically, after using RSS to capture, to retrieve packet from a multiple queues of the NICs, of the network interface, it can dispatch traffic across different threads or application, or socket, or processes. The new notion instead that is introduced is the notion of group of sockets. Basically, application sockets join a specific group, and all of them receive a quota of the overall traffic. This is the way of splitting workload across different workers and enabling parallel computation. The way, of course, packet is dispatched across sockets should have some reasoning, should be some reasonably tailored to the application needs. For example, in Linux, the Linux socket, we have several ways, several modes. They are called fan-out modes. The most reasonable is the default mode, which is called hash. Basically, there is a hash which is computed over the network layer header and optionally on the transport layer header, and packets are then delivered to the socket accordingly. Other fan-out are less useful. At least the hash one the hash fan-out mode allows to preserve flow consistency. And this is very important, for example, in the packet application, in the packet spectrum application. Other modes are less useful, and I just reported for completeness. Now, so the underlying framework and the I/O framework, even the standard Linux sockets support that. But from the application point of view, we can say that most of today's network applications are still single-threaded. And mostly, they use pcap, and the pcap library to access live traffic. So this is, we have an underlying level, the captured socket, and then we have the libpcap interface. Pcap are very useful. It's well known. I won't spend a lot of words here, but it's very convenient to use the pcap library because hides low level details, provides a convenient interface for retrieval and handling, and it includes a Berkeley packet filter for pre-digesting traffic and filtering, and as such is called portability because basically we have pcap and we providing a unified interface basically, and pcap implementation exists for most operating system, most platform. You can basically port an application over different platforms. However, at the moment, pcap library lacks for native support for multi-thread programming. That means, for example, that suppose you have, for example, an application which is multi-threaded, or a multiple instance of application. Although the application is well designed with multi-thread, so the application can potentially cope with different quota of traffic received from application, from the network card, the use of pcap basically makes all of these threads receive an exact replica of the traffic. So there is no actual benefit in splitting the workload across the workers. Same story here, of course. What we want to do instead is to take advantage of what the underlying level, say the framework, the framework provides, that is the pcap support, even to pcap. So we want to extend the pcap library by implementing a new one that supports packet one-out while still preserving backward compatibility. The pcap must be still a pcap, useful, that can be used normally. This way, for example, in the same situation as before, we want the overall traffic here to be split across two threads, and the same story here about the applications, about the reduced instance of the applications. Now, the overall work here involved a major rewrite of the pcap library, and of course it's not easy to show here. The only thing that we can show to the user is actually an extended API, which is this. This is a call to a function. Basically now once you have the pcap descriptor, you can define the group ID, the group of monitoring of where the traffic will be taken, and a string which is the fan-out, which is the mode. So you can say, for example, in a Linux socket you can have hash, random, QM, and so on. Okay. So, if you have to write a new application, you can use this, and that's it. So this solves the problem of handling parallelism for new application. But what about legacy application? Suppose you have an application which is, you don't want to rewrite the application. You don't want to make multi-thread an application which is not, it takes a lot of time. Maybe it's not even useful, and it's just too cumbersome. In some cases, you don't even have the code, you have the binary. So how can we actually enable parallelism for legacy application using this new pcap library? Basically, we can still do that. We can preload the new library, okay, outside the application itself. But then we need to do something. What we did is to leverage on the environment variables and the configuration file to instruct the pcap layer to take advantage of the fan-out that is enabled now to send to the a plain application. Application which has single thread can still be parallelized in a sense by means of instantiating different, by launching different instances of those applications. The problem is that you can change the application, so you cannot use that the standard API, so someone else should do that. And there's a configuration file that can do that. Basically, we have an environment variable which is called pcap config, which is, if it's set, it contains the path to the configuration file. The new pcap library, in the internals, specifically the function pcap activated, which the user don't see, but it's internal to the pcap library, looks for this environment variable. If you find it, it contains the configuration file, and so it parses it, it parses it, and you operate accordingly. For example, how does the configuration file looks like? Basically, is a sequence of key-value pairs. Okay, so the typical keys are the group, the for group, the fan-out, some things more specific to monitoring application, like the cap len, the group which is specified over some iterative interface, and so on. By using the configuration file, you can enable different fan-out modes, for example, for different groups, and notice that, however, some of those options can still be passed in line with in the command line with the application itself. For example, in that case, we can tell the application foo to monitor traffic over the group 3, and by using the fan-out RND, the random. When we have this variable set in the command line, those variables overrides the one in the configuration file, just in case if we have. Oh, so this basically solves the problem for legacy application. The problem is that still, this is for Linux socket, for the Linux standard socket. Sometimes Linux socket is not enough when the packet rate is too high. So sometimes we need to use accelerated framework, like the one that I mentioned at the beginning, the PDK, PFQ, PFRing, and so on. What happened in that case? Although in this scheme, those layers looks to be, well, disjointed, looks like orthogonal. Actually, what is in there must reflect the feature that are provided by the layer, the underlying layer. And so some integration is needed, some work is needed. In our work, actually, we integrate the libpcap interface with a specific accelerated framework, which is PFQ. And we do that because, first, we did PFQ, so we have it at home, so it's easier for us. And second, because PFQ actually is very well, is devoted actually to fan-out, to programmable fan-out. So it looked it looked as reasonable to start with PFQ. The use with PFQ is, at the end, is not really different than that. The API is unified, so you can still use the same way the pickup with PFQ. Typically, we can just when the name of the device in which you are supposed to get traffic is we have PFQ, the string PFQ, with column. Basically, the PFQ acceleration is enabled, and then for the rest, more or less, the grammar is still the same, as the one I showed before. The fact that PFQ supports programmable fan-out actually gives us some more option, because the fan-out string actually in the use of PFQs can be a real program. Program in PFQ is basically embedded in a string and then compiled in the module. But so this, for example, can be a real program which is written in a functional language, and can be passed to the underlying IO framework. Why we use, of course, we can do that for PFRing, we can do that for NetMap, just matter of integrating them. need to put the ends on the code integrating. So, but in principle, this is feasible. Okay, just to show you, I won't go, of course, over this, but just to show you that the fan out of PFQ, the fan out modes in PFQ is much richer. So we have a lot of functions that can be used. All of them can be passed in the fan out string and can be set to receive packets accordingly. Now, let's have a look at. Now we wanted to use it in some practical cases. And so we have this very easy, very simple experimental result. Experimental setup. We have two servers with 8 cores each and with an Intel 10 gigabit network interface. And we wanted to use two very common applications that use pcap. So we decided, we chose pstat in honor of the conference chairman, and we use the very famous BRO and deep packet inspection system. What we measure is the packets that are received by the application itself and the number of packets that are received on the interface. Basically, those two metrics, in a sense, measure the first one, how does packet fan out improve performance, and the second one is more related to the I/O framework, so when we need acceleration or not. So let's start with the first experiment. They're very simple experiments though. So in the package, we generate UDP synthetic traffic played at 10 gigabit per second speed. The average packet size was 300 bytes, and we with up to 4,096 different flows. We wanted to see how this stack analyzes this traffic in streaming mode. So we have the blue box is tell us about the percentage of packets that are received on the interface, and the cyan box instead reports about the number of packets that are actually processed by the application. So you can see that with this kind of traffic, the Linux socket, which is used in this case, is capable by itself to receive all packets on the interface. Pstat, one instance of Pstat is able to process about 50% of the packets. When we have two instances of Pstat, we are basically reach 100% of packets. Okay, so that's basically tell us that the fan out options of pcap is enough to let the application analyze all traffic. Now we want to make the system in Pstat life harder, so we decrease the number, the average packet size. So we increase the packet rate, basically, 8.2 megapacket per second, and now we see that the Linux socket itself is not enough. We use this, the Linux socket cannot, don't let us receive all traffic on the interface. Still, this start with two instances, this stuff basically we can process all packets that are actually received. The problem is that we don't receive enough packets on the interface. So we can accelerate, and we use PFQ instead of standard Linux socket, and we have this. Okay, this is not something that I understand why this happened. Shouldn't be like this. Yes. I lost this. Okay, now see, when we accelerate the I/O framework, now we can receive 100% of packets, and this stuff consistently scale linearly with performance, and with 3 instances, basically you can process all traffic. Now we go to another application which is more computation intensive because it does like deep packet inspection. So Now we use real traces, so including UDP and TCP packets. We played this trace at 10 gigabit per second, which makes about 2.4 megapacket per second, and use with Linux socket. Now, we have, the computation is too expensive now, and so we need a lot of cores. We don't have, because we have at maximum 8 cores on the system. So we had to enable the hyperthreading. Although, I mean, hyperthreading virtually doubles the number of cores, but this is not like this. Instead, actually, we see that as soon as we have real cores, which is up to 7, because one core, one real and one virtual are devoted to underlying capturing, the performance of the application, so increasing the number of instances, scales linearly the performance, but then at some point saturates. Actually, it saturates even because the Linux socket itself is not able to take all the traffic on the interface, which saturates around 60%. Again, if we accelerate the underlying framework, we have this thing. Basically, we receive all traffic. We have linear scaling until we have real cores. Then, when the cores becomes virtual, I mean the hyperthreaded core, we still have a linear scaling, but the slope is much lower. So we assume that if we have a better server with more cores on board, we can have this. Or at least we can push the real linear behavior much farther, and then with the hyperthreading we can reach the full 100% of processing. Now, basically this ends the presentation. So what we did is, overall to summarize, we extended the pcap library to accommodate packet fan-out for software acceleration, for acceleration of processing. The library is backward compatible, it's fully compatible with standard pcap. For example, if it doesn't find, if the pcap doesn't find the configuration file, it drops back. It rolls back to the normal pcap behavior. It's released as open source and is available for download at those 2 sites. And we perform some easy, simple tests to see if the performance and the results are pretty much consistent with what we expect. That's it.
Okay, thank you.
Are you when you're running multiple copies of, say, tstat or bro, is each copy started separately, or is the library forking copies of it, or how is that managed?
Okay, the bro as a can run in 2 ways: a standalone and a cluster. And a cluster configuration. It runs in cluster configuration. So there is a bro controller, which actually in which you specify the number of instances that you want, and you can. So it starts.
Multiple.
By the way, the bro can already has a sort of support of fan-out as well, but it must use natively Linux sockets or netmap or maybe PF ring, but you need some external plugin. You can use pcap only standalone configuration. In this case, we can use pcap configuration. Pcap only even for classic configuration.
And does could you run this fan-out in a mode where you have, say, several individual processes and one can crash and you can restart another one which will replace it? Because it's kind of acting like a load balancer across.
I don't know if you can relaunch one that crashed separately. Maybe, but I'm not sure about that.
Okay.
Honestly,
but would the framework, would it would the fan-out allow it if the application was coded appropriately?
There is this bro controller. There's a bro controller.
I'm more interested in whether the libpcap modifications allow it rather than the specific.
Yeah, yes.
Yeah.
question.
Yeah.
Did you also modify TCP dump?
No, we actually the objective of this paper is not to modify at all.
Oh,
application.
but have you tried it with TCP dump?
Yeah, of course.
Wrapper
Yeah.
or-
We capture separate quota of traffic over TCP dump. Yes.
Mhm.
Of course, you can. I mean, if you have the code like in TCP dump, you can compile it against a new library or just preloading the library from externally.
So if you run 2 TCP dump instances, you will get half of the flows in one dump and half
If
of the
they
others.
join the same group, yes.
Yeah.
Or if they join the same group and the fan out mode that you enable is lets you more or less split the traffic half and half. I mean, it depends on which kind of fan out mode. For example, the hash depends on the kind of flows that you receive. If you receive packets only from one host, basically you don't have this 50-50. With a load balancing mode you do, but then it doesn't preserve flow consistency. So for TCP dump is okay, but for example for monitoring application it wouldn't be okay because you have to keep the same flows on the same instances.
Can you fan in traffic from multiple interfaces and then fan it out to multiple
Yeah,
places?
yeah.
Okay. So you
For
can-
sure with PIFQ, I don't remember if Linux Socket allows that. For sure with PIFQ, and actually there wasn't I maybe ran too much here, but there was an example somewhere. For example here, see, you can get from ATH0 and ATH1, and then you can specify different kind of group. 42 is the default group, and you can say group ATH0 is 11, so 11 will be joining the ATH. I mean, you can receive packet from ATH1, and it will be
Okay.
group 11. In ATH0 it will be on group 11, while the one in ATH1 will be on group 42. So you can have all these things.
And it's a quick follow-up. Have you done any tests or experiments with multi-socket systems that have
Yeah.
non-uniform I/O paths on them?
No uniform mean which means
So like where some of the interfaces in the memory are like bound to different sockets, so memory access is not consistent in the system.
We in our experiments actually we didn't have any this kind of problem. We didn't notice at least.
So the kernel module, the PFQ kernel module that you developed,
Yeah.
the hook for that, where you're intercepting the traffic, is it happening before IP tables or is it happening after?
There's no IP table. I mean, it's
No, I know you're not using IP tables. I'm saying that within kernels, the code space is IP tables first seeing the flow of the packets, or you're seeing after.
actually we're sitting behind, aside. We have we intercept the code of the driver, the system code from the driver, and they have been overloaded. They've been overloaded. So you basically don't go through the kernel. But then you can get back on the kernel. I mean, one of the endpoints can be application, interface, or kernel as well.
Thank you.
So finally, you can get to IP tables if you want. But
Did you implement some wrapper for other capture frameworks such as Pfring or libpcap?
no. If we want to instrument the pcap to work with DPDK or other, you have to put your hands in the pcap and write them.
Because I guess Pfring already has some wrapper for pcap.
Yeah, but
Maybe
it depends. There's different flavor of PF-ring. There is the standard PF-ring does. PF-ring zero copy, I don't remember if it does. Even NetMap actually have exposing the pcap interface, but then it depends on the fan out they implement internally.
Yeah.
That's the big issue.
Thank you.
two more questions, if that's okay. On slide 17, I was curious why the link rate goes down if you have two tstat instances, and then it goes up if you run feeds.
Well, that's a good question. Those numbers are actually taken on average, so there might be some little fluctuation. I don't have a clever answer, actually.
Did you run this once, or did you repeat it multiple
Yeah, we
times?
repeated several times, and sometimes, well, the system, actually, the old capturing things is far from being linear. So everything, things may happen, and fluctuation like this basically are nearly, they may happen. So we don't have a real answer. I know we've noticed that, and we try to find a clever answer, but we don't.
So this is the mean of multiple repetitions
Yeah.
of experiments. So you
Yeah.
would have some confidence interval if you would.
No, we didn't plot them. we didn't even calculate them, honestly. But more or less, the average of that.
Okay, so the final and really interesting question is, I guess, will this be integrated into the mainline PCAP library for everyone to use easily without compiling themselves?
Well, the PCAP, if you go on the site and download the library, you can use it as normally as a PCAP, or you may want to use the new feature, or you may want a normal PCAP. It does work perfect as a PCAP. If it's going to be integrated in the mainstream PCAP, it's not up to us. It depends on the guys that would decide that.
It's a good feature, so I would think that it would be.
We try to propose that.
Okay, if there are no more questions, let's conclude this session. Thanks to the speaker once again.